Good evening to all of you. Session, I would like to demonstrate a simple problem involving a mixer and also two important tools that we will be coming across in any process simulator will be introduced in this session, namely the sensitivity analysis and the design spec. In fact, if you look at this problem, you can see that the problem is quite simple. Two input streams are getting mixed to give rise to one output stream. In this problem, I am only trying to address mass balance, so the temperature and pressure are not going to affect your result. So you may presume any temperature and pressure for the input streams, though it is not mentioned here, they are not going to affect your result. For example, if you try to solve this problem analytically, you will be in a position to write the overall mole balance. The feed rate plus recycle rate should be equal to the product rate, either in terms of mole or mass. And similarly, we will be able to present the component balance either with respect to isobutane or isobutene. So I am proposing isobutane component balance F into 0 because there is no isobutane in the stream. R into 0.2 should be equal to P into 0.05. So we have two equations and we already know F is equal to 100. So there are only two unknowns in this problem, R and P. So we should be able to solve these two equations quite easily. And if you try to solve, the analytical solution is around 33.33 for R and P will be 133.33. Now before going into the simulation, you try to analyze this problem. We have already seen that the simulator, whatever models that you are able to see in any process simulator like Aspen, are capable of doing only rating calculations. Problem. You know that the input streams will have to be completely defined along with the necessary equipment parameters for the model. Unfortunately, in this problem, we don't know the recycle flow rate and the information that is the product composition cannot be utilized while defining the problem. So this is typically not a rating problem, but maybe it's an analysis problem. So in this particular case, solving this kind of a problem using a rating model, what you need to do is convert this rating problem into convert this analysis problem into a rating problem by assuming the necessary inputs that may be required to complete the problem definition for a rating problem. In fact, though we are required to calculate the value of recycle and product, now unless and otherwise we have the recycle flow rate, we may not be in a position to complete the problem definition for this simulation. So we may have to start with an assumption for the recycle flow rate, solve the model, calculate the product composition, compare it with your required composition, and if the required composition is not met, you need to go back and assume another value for recycle. Probably if you try to do this manually, we will never be able to probably come to a convergent solution after performing quite a number of iterations. So in order to handle this type of calculations, we have two important tools, namely sensitivity analysis and design spec. Probably in this particular demo, I'll be showing you both sensitivity as well as design spec tools while simulating this simple problem. Now let me go into Aspen simulation. So the first step in any process simulation is to define the components that are involved. For example, let me call the first component as IB, isobutane. And the second component, I am naming it as 1B because it is the alternate name for isobutane is 1-butene. You can check up maybe later from the component list, you should be able to identify this. So having defined the components, you go to the next input step. So choose a property model. As I am interested in solving a simple mass balance problem, the property model also is not going to affect your results. So I am selecting an ideal property model. Go to the next input screen, choose simulation environment and create your flow sheet as depicted in the problem. So we have only one simple model like mixer. Add input and output streams. This is for convenience. Let me also rename these streams to demonstrate these two tools. This is the feed stream, and this is the second input stream is the recycle stream, and the product stream, I'll name it as prod. So once you complete the flow sheet, now you can see from the left hand side that you need to address these two red dots in order to complete the required information for completing the problem definition. So you can expand these and see that the simulator is asking you to provide information with regard to feed stream and recycle stream, but it is not asking information with respect to the product stream. Typically, in a rating model, given the input streams and equipment parameters and operating conditions, the model will be calculating the product or the output streams. So even if you forcibly open this product stream and enter the information about its composition, that would be ignored because you are using a rating model. And in addition to this, you are asked to provide some information with respect to the block, but you can see in the case of a mixer, you don't have to provide any information because it is already ticked with blue color. So now, if you are able to specify the feed stream and recycle stream, you will be able to complete the problem definition. And we have already seen that the degrees of freedom for any stream is given as C+2, where C is the number of components involved in that. This is based on Gibbs-Duhem equation. So let me go into the next input screen. So obviously it will be asking information for the feed stream named as feed. So as I said, you can assume some temperature and pressure because it is not going to affect your result as far as this mass balance is concerned. And we know the flow rate of feed stream is pure isobutane at the rate of 100 kilomoles per hour. Now, how many values did we define? Temperature, pressure, and the flow rate. So we were able to take care of C+2, one component and two variables. That's why we satisfied this feed stream. Similarly, go to the next input screen. Now it will be asking information with respect to the recycle. Again, you can assume whatever may be the temperature and pressure. And we know the mole fraction, the composition of this recycle stream, which is given in the problem statement as 80% isobutane and 20% isobutene. Right? Now you can see still this red dot is still on. That means the required input is not complete. We were not in a position to specify the stream completely. Because there are two components involved in this problem, how many variables must be defined? 2 plus 2, 4. You may feel that we have defined already 4 variables, but remember, one of these mole fractions is not independent. In a binary system, once we know the mole fraction of one component, we will be knowing the mole fraction of the second component. Anyway, you can press next. So this is the problem. When the mole fraction or mass fraction or volume fraction is given, unless and otherwise you specify the total flow, you will not be able to satisfy the degrees of freedom. As I mentioned, this degrees of freedom for a stream is based on Gibbs-Duhem equation, which says whatever may be the number of components involved in the system, you need to define at least 2 variables in order to define the state of the system completely, provided you know the total initial masses of each and every component. Now from the mole fractions, there is no way you can know what are the quantities of these components. That's the reason why when you give the mole fractions or mass fractions, you need to specify the flow rate. So this is what is meant by converting an analysis problem into a rating problem by assuming the flow rate. Probably people may laugh at us if we try to solve problems in this fashion, right? We are required to calculate the recycle flow rate, but we are starting with an assumed answer for this recycle flow rate in order to simulate this model. Especially this is because we are using a rating model. Now you can see the required input is complete. We should be in a position to run the simulation and obtain our results. Of course, you can see the results in many ways. You can look at the stream summary. You can just check up with other values. What we are interested in is with respect to mole fractions. Now this is the value that we have assumed, and based on this assumption, we got the product composition as 90% isobutane and 10% isobutene. Now this is not what we require. We wanted to obtain this at 0.95 and 0.05. So how are we going to solve this problem? So because we started with an initial assumption, let me make another assumption for this, maybe some 50, and run the problem again. So if you look at once again the summary of the results, now earlier it was 0.9 and 0.1. Now we are slightly close to the required result of 0.95. So do you think you will be able to solve the problem like this each time, assuming the flow rate for the recycle, solve the problem and simulate the problem and look at what is the composition obtained. Accordingly, you need to probably go back and adjust the value of the recycle. As I said, this problem was much easier to solve by hand, but because you are using in a simulator a rating model, and we are dealing with an analysis problem, this kind of an iterative solution is going to be mandatory, right? So in order to handle this type of calculations, I would like to introduce two important tools. First of all, let me go to this model analysis tools, expand this. Say new. So it is automatically going to name it as S1, sensitivity analysis 1. If you want, you can give your own name. Now you can see there are 3 red dots. Unless and otherwise you complete these red dots, the sensitivity analysis definition or input will not be complete. Now be careful with these two variables, vary and define. So for example, if you look at something like process control jargon, define corresponds to, see, in the case of process control, you have a measured variable, and the measured variable need to be maintained at a particular set point. For example, it could be level in a tank, level of liquid in a particular tank. So if there is a deviation from the set point, you need to manipulate some variable so that it will be brought back to the required set point. So define corresponds to the measured variable which need to be maintained at a particular level, or we are interested in looking at what is the value of this measured variable. Now in order to achieve this variable, what is the variable that you are trying to manipulate is regarded as vary, right? So in this problem we know clearly that we are trying to vary the recycle flow rate and obtain the required composition in the product stream. So you can say new, first of all you are addressing vary variable. So what kind of a variable is this? Depending on the problem situation, the vary variable could be with respect to a stream, it could be with respect to a block, it could be with respect to operating conditions of a particular unit, or it could be the physical dimensions of a particular unit like volume, number of stages and so on. So maybe in other problems you will be able to see many other examples. So this is vary is corresponding to a stream variable, a variable associated with stream. In fact, you can observe that all these variables in any drop-down list are automatically arranged in alphabetical order. So you can pick up this stream variable. What is the stream that you are trying to vary the flow rate? Recycle. So the variable that you are interested in is mole flow. Now what you can do is, we already know the solution, analytical solution. Let me say 10 to 100 in steps of 5. So instead of you assuming the value of recycle flow rate each time, the sensitivity analysis you are asking the sensitivity to do, start with a recycle flow rate of 10, calculate the product composition, and increment it by 5, calculate the product composition until you reach the value of 100, right? So we have defined this vary variable. Go to the next input screen by pressing N. Now what is the defined variable you are looking at? You can name it in your own way according to your convenience. Let me call it as something like PP, product purity. You can give any name of your choice. Now this is also a, because we are looking at composition. See, remember there are some variables, sorry, let me click on stream variable. So here you can see mole fraction directly, and similarly mole flow also is available here. But if you select the mole flow, we did not do this in the previous case while defining vary variable. We went to stream variable and selected mole flow. When you go to the stream variable and select mole flow, you are talking about the total molar flow rate of the entire stream. But if you select the mole flow here, you will be talking about the mole flow of one of the components involved in that particular stream. Sometimes you may need to do this. Accordingly, you need to select appropriately. But here I am required to identify the mole fraction of one component. So let me call it as mole fraction. This is the variable I am looking at in the product stream. And what is the component? So let us say you can pick up any one of them, IV. So whatever name that I have given here, which is named as PP, is going to represent the mole fraction of component isobutane in the product stream, right? So let us say we wanted to vary the recycled flow rate, and for each of these recycled flow rates, we wanted to observe what is the mole fraction of the isobutane in the product stream. Go to next input screen because still there is one red dot. So you simply click on fill variables. Based on the definitions you have given for vary and define, the simulator will automatically take care, right? Okay. So you can see once again, all the required input is complete. So we should be able to run this problem. You can see from this control panel, this block V1, which is a mixer model, is repeatedly solved because of the sensitivity analysis. So this is the penalty you may be paying in order to analysis problem using a rate model. Why is it repeatedly solving this model 20 times? That depends on what was your start point, what was your end point, and what was the increment that you have defined. We said 10 to 100 in steps of 5. So obviously the model has to be calculated 20 times, each time incrementing the recycle flow rate by 5 units. Now you can look at the results of this sensitivity right here. So when the recycle flow rate is 10, the product purity, that is the mole fraction of isobutane in the product stream, is about 98%. As you keep on increasing, you can see that the mole fraction is decreasing. And obviously, where is our solution? When the recycle flow rate is 30, the mole fraction is 0.95, but when it is 35, it is 0.948. That means the solution is somewhere in between. So you can also look at the results curve from the sensitivity by going into the plot, click on whatever variables that you are interested. So this is how the product purity is changing with respect to the recycle flow rate. So from 10 to 100. For example, if you are interested, it may be possible to identify the value corresponding to 0.95 from this plot. It is somewhere between 32.5 and 35, right? We know already it is 33.3, in fact, the actual solution. So if you want to further refine your output, you go back to the input because we now have an idea. Maybe you can say 30 to 35 steps of maybe 1 or even 0.1. Right? So let us run this problem again. So once again, you can see the results. We already know the solution. So you can see at 32.3 it is 0.95. Sorry, at 32.4 it is 32.5. What is that? 33. We have to look at 33, right? 33.3 it is 0.95, and at 33.4 it is 0.9499. So the solution is somewhere in between. If you still want to refine the solution further, accordingly you can change the starting point, ending point, and the increment. Or you can look at the results, go to this plot on the main menu, results curve. So I wanted to plot product purity. So this is how it is going to be. Don't worry about this because we started with 50, it is taking up to 50, though the sensitivity analysis is supposed to be between 30 to 35, right? So this is how you may be able to solve the problem using sensitivity analysis. So the only reason for using sensitivity analysis is instead of doing it manually, you are trying to put it in a structured way with some starting point, ending point, and increment. Normally, we will not be using sensitivity to solve this kind of analysis problems. Now, one more thing that you can observe here, when I go to the stream summary, remember we started with an assumption for recycle flow rate as 50. Unless and otherwise I go back here, modify this flow rate from 50, I will not be able to change the results within the block. So whatever calculations that are done by the sensitivity loop is outside the block. It will not be affecting the block calculations. So if you want to affect the sensitivity, you will have to write it as something like 33.33 in order to get the product purity in the simulator as 0.95. Anyway, this normally is not used usually for solving such problems. So let me deactivate this and try to introduce another tool which is available in flow sheeting options. Click on or expand this, say new. So this is the first model that is available under this is design specification tool. So by default it names it as DS1, save OK. Now you can see define and vary were same as what you have done in sensitivity loop. But something extra is coming here in place of tabulate in the case of sensitivity. Now you are talking about spec. More or less the variables are similar. So as I defined earlier, the product purity, it is going to be similar to that. So it's a stream variable. The variable is mole fraction, stream is product, and the component is, let's say, isobutane. So the name that I have provided here as PP is representing the mole fraction of isobutane in the product stream, like what we did in the previous sensitivity loop. Now, the name that I have given for this is PP, and the value that I am interested in is 0.95, the product purity. I am interested in a value of obtaining 95% mole fraction with respect to isobutane in the product stream. Remember, this kind of information, there is no way you can supply in sensitivity analysis. But in design spec, we are interested in calculating the recycle flow rate and product purity, recycle flow rate and product flow rate corresponding to this particular purity. So you can give some tolerance. So this is what is meant by spec. That's why this is called as design specification. We wanted to obtain a particular requirement, specification. So go to next. Again, vary variable is similar. In order to achieve this particular purity, what is the variable you are trying to vary? It's a stream variable, like what we did earlier. The stream is recycle, and the variable is flow rate, mole flow. So I'll say something like, we already have the idea about the solution, 1 to 1000 or maybe 10,000, doesn't matter. What I expect to do in design specification is, I have to provide a range of values within which the solution is likely to appear. This is much easier for us compared to sensitivity. So you can start with maybe a small value and a very large value, so it will take care. So you can see once again, all the required input is complete. We should be able to run the problem. So you can see within 6 iterations, we were able to come to a convergent solution, and the method used by Aspen happened to be secant. In fact, this was the default method used by Aspen to solve any design specification problem. If possible, we will be able to see that solving a design specification problem is similar to calculating the root of a single equation in one unknown. So, you know the secant method, how it solves one unknown in one equation. The same thing you can also see. So, what about the results? See, we started with an initial value of 50 for the recycle flow rate. At that time, the product purity was 93.33, but the actual value, we said we need to get 0.95. So the solution for the recycle flow rate is now 33.333. Now be careful. When you look at the stream summary, now you can see we started with 50. We no longer adjusted the value from 50 to 33.33. And similarly, the mole fractions earlier were 0.933, corresponding to a value of 50 here. So the design specification, if you are able to successfully come to a convergent solution, will be rewriting whatever values that you have started with the convergent solution, so that these values are available subsequently in other models. This is not possible in sensitivity unless and otherwise you raise the recycle flow rate from 50 to 33.33. Now, without our intervention, the design spec was able to do this automatically, right? So generally, the design specification tool is used for such purposes whenever you have a requirement with respect to the output stream or maybe an intermediate stream connecting two units. So you will not be able to provide information while defining a problem for a rating problem. So in all such cases, you will have to deal with or use either sensitivity analysis or design spec. Let me once again go back. See, in this problem, we wanted to calculate the recycle flow rate, but the mixer model can do only rating calculations. In fact, this is true with respect to most of the models that you see in any process simulator. So because of this, what we are trying to do, this is an analysis problem. Why? Because whatever product composition that I get is not acceptable unless and otherwise it is at this predetermined value. So unfortunately, this composition I cannot make use while defining the problem for a rating, while specifying the problem for a rating, right? So first of all, this kind of problem is converted into a rating problem by assuming the necessary inputs required to complete the problem definition. So the penalty that you are trying to pay in order to solve such analysis problem, either by design spec or by sensitivity, is repeated solution of this rating model until you come to the required solution. So this is mandatory. So the same thing, in fact, you will be able to see later. In the same way, we will also be able to design equipment. So with this, I would like to stop this demonstration.